This video is going to be covering the capabilities of a Nortec 1000 flaw detector. So this tester was built in the late 1990s, so it's just about 30 years old. It's got a super bright EL display, which is electroluminescent display. Look how nice that is for 35 years old. Not a scratch on it. Anyway, these series of testers, the Nortec 1000s, the 1000S, the 1000, 1000S. Then they did the 2000, which was still a single frequency. Then they did a 2000D, which was a dual frequency flaw detector. Then they did the D+, which added a color display. And then there was a Nortec 2000D Plus EMI, and the EMI didn't really add a lot other than it was designed to meet certain requirements for not emitting electromagnetic interference, and that was specifically for the military, I guess. So if you're out there shopping for one of these used ones and you see a 2000D Plus and a 2000D Plus EMI, you can forget about the EMI and get the other one, or buy either one, but you're not getting anything extra if you go for the EMI. Now, if you look up on top of the Nortec 1000 and the Workstation 2000, which is my favorite instrument, you'll see the Olympus 600. Now that's one of the upscaled versions. So it's got all the bells and whistles of all the 600. It's got all the features of the 600, rotating, scanner capability, dual frequency, all that stuff. However, a lot of people, when they're buying a tester, like if they're on a budget, they're like, well, I can't afford a 600. Well, I think a lot of those people may not realize how much stuff you can do with a Nortec 1000. So we're going to check into that right now. There we go. First example is just a simple Olympus pencil probe, or called a surface probe, pancake probe. They all mean the same thing. So that's me tapping on my material. I have an aluminum EDM block. And I'm just going to rotate the phase around, or the angle of my impedance, trajectory, whatever you like to call it. Null my instrument. Clear the screen. And I'm upside down. No problem. We just rotate that phase trajectory around to get probe motion horizontal, or as the technical folks like to call it, the magnetic field coupling efficiency, liftoff, fill factor. But since we're doing surface, we're talking about liftoff, and that's the distance between the coil and the material. So I hit erase and I lift off. The impedance point goes off screen because the coil right now, I'm holding it in air, which means it's unloaded. There's no material to load the coil. But when I bring the probe down to the material, and I'll hit erase, and I'm decreasing liftoff, I'm slowly starting to load the coil with the EDM test block, and now you're on the operating point for this particular brand of aluminum. And now when I scan over one of the EDM notches, of course you can see the flaw. So I crank up my gain a little bit. Then let's see here. Let's do what everybody likes to do with the... No, that's not what I wanted to do. What I wanted to do was... Everybody likes to put... Everybody likes to put their null point kind of down to the right when they're doing these surface exams. And then, let's see, let's crank some more gain into it. Nice, right? Probably didn't think an old Nortec 1000S could do this. Oh, some people like to crank in the vertical gain. Well, we can do that too. Although I'm already quite high on my gain, 90. Wow. Okay, so we can go over to special. And that's even on a drive voltage setting of low. Hold on, I'm doing this in the dark. Give me a break. Let's crank it up to medium and see what we can get out of it. Most times a medium setting is enough, you know. But you'll get certain probes that you won't get the results you want on high setting of drive voltage or medium, so try low. But start high, see if you saturate. Wow, that looks good. But I got a gain of 90, so let's crank that gain down a bit. Obviously, the Nortec 1000 is handling the medium setting with this particular probe quite easily. Let's hit null, bring it back onto screen. Beautiful. Beautiful, beautiful. Loaded, unloaded, loaded, unloaded. We're going to hit erase, and we're going to go boop, 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 all three. Let's just check it out on the high gain just for the fun of it and see what we can get out of this bad boy. Can we go to high? So now I got it loaded and I'm hitting balance. Whoa! Okay, so I'm going over the shallowest surface notch, medium, there's the highest. I'm just going to crank in some gain and go back over the deepest one. Now I'm going over the shallowest flaw. So now let's do something here. Let's go to vertical position and crank them up a little bit. We'll go horizontal position. And we'll crank it over to the left a little bit. Now I'm on the material, we'll null it. Okay, so that's my shallowest surface notch. And we're going to gain a high now, right? So then I'm going to go back into the main, and I'm going to go to the vertical gain, which is here. Okay, so the shallowest surface breaking EDM notch in my cal standard is this one. And this is at a probe drive voltage of high, gain of 75. But if that's your smallest notch, I mean, just imagine what your largest notch looks like. That's probably off the screen 3 times at least. All right, so we know that the Nortec 1000, they didn't even call it an S because at the time there was no D. It was just single frequency back in the days of this tester. So now we're going to try something a little different. Everybody likes to get the 600 and do weld scanning. There's a lot of testers that are made specifically for weld scanning. Well, I could have called this tester a weld scanner because I could scan welds with it. So what we're going to do now, if I can find where I put the darn thing, is here it is. This is a plus point weld probe. It's kind of dark, you can't see it so good, but there's a line on this thing, a reference line. And the line on weld probes is so it will help you keep the orientation of the probe the same when you're scanning along a weld. And then after you scan the weld, you can rotate the probe 90 degrees and scan back. See what kind of changes you get then. So this is the weld probe. I'm going to hit null. Erase. I just want to make sure my probe's working. Okay. Something is wrong with my tester. Well, could that be the gain? I don't know, maybe. Let's crank the gain down a little bit. Okay, something is not acting as expected. So I'm gonna go and try to adjust the drive voltage to medium. And then I'm gonna hit null. Now keep in mind, I have manipulated the vertical gain. So that could sort of mislead us that something's wrong with our probe or cable, where it may have just been that I forgot to adjust my horizontal and vertical gains to be the same. That's important, so it doesn't screw up your aspect ratio. Okay, so now I'm nulling with my Weld probe, and I'm erasing, and I'm getting a little blip there, but I don't have enough gain. So now let's crank up both of the gains simultaneously. Ooh, okay, so now I got that's my liftoff line. And again, with the surface probes, you normally have loaded to the right. That means I've got that upside down. So let's crank this back around, all the way around 180. You ever hear people say I did a 180? It means they did the opposite. So that's the unloaded operating point, coil and air, and that's the loaded point. That's the operating point of my test material. Now I hit erase, and I scan over the cracks, and one moment, please. There we go. Angle. Keep in mind this is a plus point coil, so you have to scan your material with the reference line either pointing to the left or pointing towards you or away from you. Because with coil design, it's very important that you're scanning the material with your coil in the right orientation to detect the type of flaws that you're after. So because I was in the dark here, I wasn't really able to see where my reference line was. But now I'm going to take and bring this horizontal over a little bit. Okay, so to prove that we can do some weld exams, I got a weld plate here somewhere. Right there. And I'm just going to set that down on the table here. Now, my EDM notch was aluminum, or my EDM block was aluminum, and this is carbon steel, or maybe some kind of stainless. Anyway, so the impedance trajectories are going to be a little bit different. There's unloaded, there's loaded, touching the material. So, keep in mind that differential arrangement probes are less prone to liftoff. See when my operating point is in air, where my coil's unloaded? Normally that shoots way off your screen, right? But because it's differential, there's just really not that much difference. Whoa, there we go. So let me go into main and crank my angle around a little bit. Null it. I'm going to change this over a little bit for you here and bring the horizontal position over. Whoa, can you see that? That is your surface breaking crack in this ferromagnetic material. Uh-oh, what did I do there? Always be patient with eddy current and Eduardo. I was going to take the gain down a little bit so we get that crack signal on screen. There you go. You're not going to miss that one, are you? With the Nortec 1000. All right, so far we did some surface scanning with a pencil probe on non-ferrous material, aluminum. Then we just did a weld inspection with a differential plus point probe. Now, one word about the plus point probe. That particular flaw that was vectoring in the positive direction was an axial notch. Now, if I were to keep my probe rotation in the same orientation and scan past a circumferential notch, it would be vectored in a negative direction. Now, here's where it gets a little bit tricky. Let's say that I scanned back over the axial notch that you see on your display here. If I were to rotate my surface probe 90 degrees and scroll past this again, it would be vectored downward. All right, well, you're probably saying, let's show me that, because I don't believe you. All right. So here, that is with my orientation line facing to the left, or actually facing the weld. And now if I just rotate my probe so the line is facing towards me, so I rotate it 90 degrees, there it goes down. That's the dual polarity. Actually, it's single polarity, vertical down. And if I rotate, it goes vertical up. Those are both single polarity indications. Let me see if I have, I think I got a hole here somewhere. Now this is an aluminum plate. I'm going to see if I can give you an example of a dual polarity indication. There we go. See that down and up? That's a pretty big hole that I'm going over there. But both coils see it, so you get a down and an up. But when you get linear indications or preferentially oriented in the either axial or circumferential directions, then you'll just get the single polarity. Okay, what probe should we move on to next? Now, if you were using the Nortec 600, you have the option to also operate probes that have a BNC connection. Well, this Nortec 1000 doesn't have a BNC connection. But Nortec Staveley Instruments, they weren't stupid. They developed these add-ons, these little adapters here, and there's actually a couple different kinds. Now, this particular one has a 4-pin probe for like a 4-pin connector for Zetec 4-pin probes. Zetec, a lot of their instruments have different probe connectors, but they have surface probes with 4 pins. They have bobbin probes with 4 pins. The bobbin probes that they use today, at least with like the MIS 80s, MIS 80 IDs, those are all 4-pin probes. I have a MIS 27 here. You can use 4-pin probes, but the adapter cable's different. So you can't just plug a 4-pin directly into the back of the MIS 27 or the MIS 28. You got to have an adapter cable. Adapter cables aren't cheap. But if you can get your hands on one of these little adapters, and just like the 1959 edition of AS&T's NDT Handbook, Volume 1 and 2, anytime I see one on eBay, I buy it because I know that they're hard to find. And I know that somebody will appreciate them. Same goes for these adapters. I probably have at least a half a dozen of these things because they allow you much more flexibility with these older instruments. Now you'll notice on the output here, there's a switch. It says B or R. You can probably imagine what that's for. That's for if your probe is set up for a bridge configuration or a driver pickup, otherwise known as reflection arrangement. And then there's a special setting over here on the right. There's on this particular adapter, there's 3 different settings on it. And there's a little plastic card that came with this adapter that shows you how to configure the 2 different switches depending on what type of probe you're hooking up. So, just like with Forrester's similarity law, you got to have the corresponding impedance graphs to make any sense out of them. When you have these adapters, it helps a lot when you have the corresponding operator card. So now, we did the surface probe, we did the weld probe. Now it's time to hook up the adapter. So all it does, there's the receptacle here is the Lemo 15 pin connector, and it just pushes down into that slot or down into that pot, and then you screw these set screws down. Must be good enough. Okay, so the first thing we'll try is a Z-Tech 4-pin surface probe. So I'm just plugging that 4-pin probe cable into the adapter. Bridge on this one is if I'm looking at it from the front, I got to push the little selector to the right. And I just have an angled pencil probe, pancake coil, whatever you prefer to call it. Aluminum EDM notch. I have an unloaded coil at the moment, so I'm going to null it in air. There I have my impedance point from air. And now I'm touching the probe on the material. Nothing's happened. Does that mean my probe died? No. It probably just means I have to change some particular setting. So this is where we go into the experimental phase. Let's try setting the drive voltage to high. I'm not getting much result. I always get concerned when I'm getting no result on these videos, because what if I'm doing something wrong? Well, this probably isn't going to do it, but I'll check this anyway just to show you how we go through all of the different options. Obviously that didn't do anything. So we're going to go back and we're just going to set her back to medium. And then we'll try to crank up our gain, see if that does anything. Okay, it's not doing much, but I still have a couple other selector settings on here. Now, if I didn't know any better, I would probably switch over to reflection mode, which I just turned the selector at the top. That doesn't do anything, so that's probably not the issue. Then I'll go over, and remember I have that other switch. It says low, off, and high, I think. So now, I'm not getting any results at all with this particular probe. So my guess is I don't have the adapter attached well enough. So we'll see. It didn't feel like it was really pushed in high enough. You know, maybe I had one of these little strings from the battery in the way. So that's part of our troubleshooting. Aha, I think it went in a little better now. So I would say most of the time, if you take a cable and it's the right cable and you hook up a probe and you're not getting a signal, chances are the probe could be dead. Your instrument could be shot, maybe you left it out in the rain, or you probably just have a setting incorrect. This is where an experienced level 2, rather than throw the probe or the tester away, he'll just keep playing around with the settings until he gets it right. Whoa, okay, so now we're getting some life. We did a little CPR on this tester and the probe, but the instrument appears to be saturated because I can't get any signals. So that shows me my gain's too high. Now, our drive voltage was set to medium. That's about 8 volts. And that setting, I know that it's works for most applications. And it's already on medium. So I've cranked the gain down a little bit. And I know the instrument. Now you can see we're starting to get some life in this probe. Take the gain down a little bit more. Let's set some phase rotation on our liftoff. Okay, I know that my liftoff's upside down because when I pull a probe off, the impedance point goes to the right, but that's opposite of what we want. So here's where we do the old switcheroo. Put our liftoff back to horizontal. Now the loaded coil impedance point goes to the right. So we're going to hit null. and then erase, and now we got some action. There's the largest EDM, medium, and then the smallest one. All right, so there's a Zetec 4-pin probe. Now, if I was using the Nortec 600D advanced model, and I wanted to hook up a probe with a BNC connection, and that's a coax cable, there's actually a setting in the operator selectables where you change the connector type from Lemo to BNC. And I've seen with that instrument, whether or not you change that setting, you may get some active signals, but there are other times when you actually have to have it selected for the probe to work. So now I'm going to be hooking up. This is another Weld inspection probe. This one has a little surprise I'm not going to tell you about yet. But it does have the coax. So I'm going to hook that up to the same adapter, which has a little coax port on it here. Hit erase, and I'll hit null just to get our unloaded coil operating point. There it is on the screen. Okay, I'm tapping the probe my material, nothing. Do I throw the probe away? Now you know the answer is no. Well, let's go and try a couple things that won't work at all. I changed the drive voltage to high. That doesn't do it. Let's go in here and let's change. You know, sometimes this drive voltage does weird things. Just go check them all out. And even if they're the obvious wrong choice, at least if you try them out, then you'll know that you ruled that option out. And it's maybe one more reason that leads to your decision that you need to try some other variables or settings to save the probe's life. Because this is a perfectly good probe. So I've tried changing my drive voltage. I could try taking my gain up a tad. That's not going to do anything because this probe seems to be dead. However, remember that selector on the top of our adapter that says B and R? Well, the R is for driver pickup, or more specifically, reflection mode. So now I got on reflection mode, but I still have this other selector switch in the back. And where is it? Right here. Okay. So now that I've got the right selector switch setting, maybe I go and adjust my voltage again, my drive voltage. Ooh, we're starting to get some life. Starting to get some life in this probe. But something's still not right. I'm going to try some different selectors on here, different positioning. I'm actually going to try, let's see, reflection. I'm going to try, just to see if it makes any difference, to go to high drive voltage. And I'm going to null on my aluminum. One moment, please. I'm in the dark. It's still morning time. Erase. Ho! So we adjusted the drive voltage to high. So obviously that's what this particular coil likes. And then we, on the adapter, we switch it to the reflection mode because this is a driver pickup probe, which means it has a driver coil and a much smaller pickup coil inside of it. And then we had the choice of high, medium, and low on our selector. That's the, I think, the high setting. So now if I scan my material, getting some action, I'm going to null it again. And then I'm going to adjust the angle. So we're going to adjust liftoff. Now this one has a lot of liftoff because this is not a differential arrangement. So if my impedance point goes to the left when I lift off, the phase is set correctly. So now I'm back on the material. I always like to hit null, just for the heck of it. Hit erase. And now I'm going to start with the smallest EDM notch, medium, and then high. And of course I still have some gain options left here, so I can go a little bit higher. Now when I scan over the shallowest surface breaking notch, that was the medium, and then that's the high, right there. Okay, so we went over a regular surface pancake coil, then we did the Weld probe, then we did a Zetec 4-pin surface probe, now we did a driver pickup Weld probe. Wait a second, you're probably going to want to see if we can do a weld with that particular Weld probe. So that's our ferromagnetic material. So all I really have to do, I'm not even going to change the frequency, but I'll just have to change my phase setting a bit. So let's just null it. And before I adjust phase, I'm just going to scan the material real quick. Boop. There's your flaw right there. So we'll wow, this thing does a really good job with that one. Crank the gain down a tad. We'll hit erase. I don't know, can you see that? I can see it. My vision's not even that good. Good enough to be an analyst, though. You only got to have J1 in one eye. I used to have a buddy, RIP. He used to analyze data with a patch over his eye. And I have no idea how he did that, because you'll get a headache looking at data with two good eyes. There's your flaw right there. All right, so now we know that that works for weld inspection. And last but not least, I have a bobbin probe. So we're going to try that one next. And for this one, I'm going to take the adapter back off. Then for the bobbin probe, I actually have just an adapter cable. So this is the 15-pin Lemo that connects to the back of the Nortec 1000. Got a core star, barnacle scraper, bobbin probe. So this may take some adjustment also. We'll have to see where we're at. Okay, we got some kind of saturation thing going on here, so we're going to have to go into probe, and we'll take that down to medium, the probe drive voltage. Go to main, we'll hit null, erase. You know, if I get this far and I can't get the bobbin probe to work, I'm going to be super disappointed. I will be super disappointed if I can't get this to work. I don't usually give up though, so I probably will get it to work. Null, let's hit the null button. See? Persistence always pays off with eddy current. If at first you don't succeed, keep trying. Now, the particular configuration I have set up, I'm seeing the absolute signals. But if I pull it a little bit slower, there's my 100 right there. And then, no, I take that back. Hold on. No, I was wrong. That signal you see there going to the left, it's actually a tube support plate. Tube support, 100, 60. Let me crank in a little more gain. Tube support, 20s, 420s, 60%er, and there's our 100. So what that tells me is that we can probably manipulate our probe noise a little bit. And now we'll hit erase. Tube support plate, 420s, 60%er, 100%er. So now you have seen that the Nortec 1000, the first generation of the Nortec portable flaw detectors, is a very capable instrument, even though it's almost 30 years old. Please like and subscribe, comment below, tell me what videos you would like me to make. Thank you.